Hi, my name's Steve, and I'm going to talk about the new features in WhirlyGlobe-Maply version 2.4 and future versions. So here's what I'm going to talk about. I'm going to do the introduction, which is what I'm doing now. Then I'll talk about the history of the toolkit and the people who contribute to it. I'll talk about some interesting features as well as some boring ones, and with each of those, I'll give you a sense of where we're going to take that feature. So if you're not familiar with WhirlyGlobe-Maply, it's an open source, mobile-first geospatial toolkit. And what that means is it's Apache 2.0 licensed, that's the open source, and that makes it very friendly to use in commercial apps. It's based on OpenGL ES 3.0 or 2.0, which makes it very, very fast and lets it do a lot of fancy things. And it can do either a 3D globe or a 2D map, and it's available for mobile devices like iOS and Android. Now we've got four main sets of customers. We've got the weather apps. These are apps like Dark Sky. There are map display apps like Gaia GPS. There are aviation and other aerospace apps like FlyQ EFB. And there are education users as well, like National Geographic World Atlas or Stratologica. The toolkit is more than 5 years old at this point. And what you can see from this is that we've been steadily adding features, and we've also been taking longer to do it. The time between 2.3 and 2.4 was quite considerable, and we're going to try to cut that down in 2.5 in the next version. The toolkit's gotten pretty large. It's up to 134,000 lines, split between a core library and an iOS and Android interface. In addition to myself, we have two contractors who contribute regularly to the toolkit. Jose is based in Spain. He's done a lot of the Android porting as well as some of the infrastructure work. And Ronan is based in Toronto, and he's done a lot of client work as well as interfacing to other systems like Eris Weather or Mycello or others. And we're also looking at hiring in the next year or so for full-time engineering. Now, my little company is mousebird Consulting, and it's mostly a consulting company. That's why it's got consulting in the name. It does OEM deals as well, where people take the toolkit and use it for high-performance rendering in their own systems. And we do provide support contracts for iOS and Android, and that's where we answer questions in a timely fashion and fix bugs, do training, that sort of thing. But mostly we do consulting on other people's apps. For the rest of this talk, I'm going to talk about a specific feature in the toolkit, how it works now, how it works in the new version, does it work on Android, and where we're planning on taking it in the future. But before I do that, let's talk about how things are going. The short answer is that things are going well for the toolkit and for the company, mousebird Consulting. People aren't necessarily aware of what we do, but our users have been very successful. And here's an example. This is a screenshot from Apple's store. If you go to the iPad mini 4 page, this is what you'll see. And on the lower right, you've got a screenshot of Dark Sky, one of our most popular users, and that's WhirlyGlobe right there. That's a standard WhirlyGlobe temperature overlay. It's really quite beautiful. Now, people might recognize Dark Sky here, but they definitely won't recognize WhirlyGlobe-Maply, and that's something we need to work on. But on the positive side, our customers are doing really well, coming back for more features and porting to Android and doing all sorts of cool stuff. We just need to work a little bit on outreach. So let's talk features. In version 2.5, we've added Swift support. Swift is a new programming language from Apple for iOS, and it's intended to make things a little easier to use. Now, Jose got really excited about Swift, and he added Swift bindings to the toolkit. And here's an example of loading a MapZen vector tile layer just using Swift. He also added Swift examples to the tutorials, so you can look at either Objective-C or Swift code when you're working through the tutorials. And that turned out to be quite nice. People are starting to use Swift, and we're getting some good feedback. Now, I wasn't super excited about Swift because I've been doing a lot of Android development over the last year and just don't have the time to think about it. But I did get an opportunity a few weeks ago. I went to one of these hackathons for space apps and met up with a user experience designer, Ali, and she was able to code in Swift. So she built the user interfaces and then wired them up in Swift. So I switched to Swift to accommodate that. and I got to work up close and personal with the Swift bindings in WhirlyGlobe-Maply, as well as get a sense of how they worked with the rest of the iOS system. And I have to say, I was quite pleased. It was pretty pleasant to use, pretty easy, and I was impressed that it seems to appeal to your non-hardcore developer types, and that was very, very interesting. They seem to have achieved one of the goals they were going for. So we built this neat app in about 48 hours, and it's almost entirely Swift, and I hope to use Swift more in the future. Let's talk about some core features. One of them is image base map paging, and this is where we take a remote base map hosted somewhere in the cloud. We load individual tiles, stitch them together, and make them draw really fast. This feature has been in the toolkit for a long time. It's probably the most commonly used feature. We also do the same thing with data overlays. So this is it's basically the same thing, except it has frames of animation, which we're interpolating between, and we can load those frames individually over time. We can let you control how it's being animated. You can put your own custom shader on it, all stuff we've had for a long time. One feature we've added is a ramp shader, and what this is instead of displaying regular color data, we take a more raw data, like basically data values from 0 to 255, and then in the shader itself we turn those into colors. And the nice thing about that is that it's more compact. You can send the data to the device in a much more compact form. In memory it's just a byte instead of 4 bytes, and then you turn that into a color using just a texture, and that means you can change the texture. You can reuse it for temperature versus clouds versus radar or what have you. It's very straightforward, and it's something we've explicitly added to the toolkit in the last version. But the really big news is that all this stuff is available on Android as well, from your basic base map approach to your animated overlays. That's all there on Android now. In the future, we'd like to improve the interpolation. So if you're displaying a map, you probably don't notice this, but if you're displaying overlaid data on that map, like radar data or clouds or what have you, if you get up close and personal with the pixels, you'll see bilinear interpolation artifacts as on the left. What we'd like to do, and make this standard, I should say, is to switch to bicubic interpolation, which looks a lot nicer when you overzoom the data. I've done this a couple of times now for customers, and I like how it looks with their data, but we'd like to make it generally available. Another feature we'd like to fix in the toolkit is edge stitching. Now here's the problem that is causing this. If you take a big map or a big chunk of radar data and you chop it up into little pieces and you send those pieces to a mobile device, if you stitch those pieces back together exactly as they were, it'll look good. But if you do anything even a little bit different, you're going to see problems. So if you overzoom the data, you get too close to it, as in the upper right there, you'll see discontinuities where there's linear features, or if you're doing some fancy interpolation as on the lower right, you'll see discontinuities at the edges. This is fixable, but it requires a bit of shader math, and it looks like devices are now capable of doing this without wasting too much of the GPU. So we need to do some shader math, we need to use a bit more memory, and there's a lot of internal logic to make it all go. But we'd really like to fix this problem in the next version. So let's move to 3D for a moment. Even though the toolkit is nominally 3D, most people use it in a 2D mode. They stack up their data layers and they look at their data top down. And what that means is that even if it's on a globe, it's basically just a map. But we do have users doing true 3D display, and here's an example. This is an app from the National Air Traffic Control System of the UK, and they've got 3D models for all the commercial air traffic in the air at the current time. And those models will move around. They'll animate from position to position, and they'll update occasionally. And point being, we can display 3D models now. In addition to your regular 3D models based on wavefront OBJ files, which I believe is a format that's old enough to vote, you can also do models that you build yourselves. And this is useful when you have data that's always different. For example, for airports, if you need to build a specific airport runway, you can now do it with a model builder. So you build up your rectangles, your chevrons, your text, and then you present that all to the system. It'll make it efficient and then plunk it down wherever you say. And you can also extrude shapes. And this is nice for data that isn't always fixed. So airports change as you get close to them. Each airport is different. You might have arrows or extruded data, which represents some specific data value. It's very nice for generating this stuff. And the models can also move in real time. So we do the correct instancing at the OpenGL level, and we can also, the shader also allows them to move, which means that you can have a lot of them being displayed at once. At present, there's no model support on Android. In the future, where we'd like to take this is to support the GLTF model interchange standard, which is hopefully gonna replace a lot of things like wavefront OBJ. It should be fast and efficient. We'd like to do better shading and transforms in the toolkit, and I suspect we'll add more model builder functionality as well. Let's stay with 3D and talk about terrain. Now, the toolkit has supported 3D terrain databases for quite a few versions, but they were in this local terrain format, SQLite, with blobs of data for the tiles, and they had to be built with custom tools. They were open source, but they were still very custom. Now, the only people doing this were really the aviation users, because they had the wherewithal to gather all the data, process it, build the databases, get them down to the mobile devices, and they really had a big need for that. We're trying to make this easier, and to do that, we've started supporting the Cesium terrain format. Now, Cesium is an open source toolkit for JavaScript that does a very Google Earth-like globe. They have some really nice services backing it, and one of them is their 3D terrain surface, shown here. Now, these are tiles of tins, triangular irregular networks, and what that means is that they look a lot better than a grid for the same number of points. And the data itself is really quite lovely, but you might notice that we're not overlaying imagery here, and I'll explain why next. The way Cesium terrain is organized is different from the way your normal spherical Mercator TMS-based tile source is organized. On the left is what a regular tile source looks like. It's got a single tile at level 0. This is what you might get from OpenStreetMap, Mapbox, Bing, Google Maps, what have you. The Cesium terrain has 2 tiles at level 0, and though this makes sense spatially, it breaks the Earth down more efficiently. It means you can't overlay one on the other without doing a little bit of work. We'd love to do that work, but we're waiting for a customer who actually needs it. And as for Android terrain support, it's not there yet. In the future, we'd like to support the Cesium terrain better, also maybe support materials, and support some other sources of elevation as well. Now, WhirlyGlobe-Maply has done vector maps for a long time. It does labels, markers, lines, aerial features filled with or without textures, all sorts of crazy stuff. It supports a variety of input formats, and particularly among aviation users, they tend to have their own custom data formats, SQLite databases, or who knows what, that they're turning into vector maps on the fly. So the toolkit has been able to do this for a long time. And to make it a little bit easier, we support things like wide vectors. Now, there's a couple of ways of displaying vectors in OpenGL. One is you can just display lines, and they work fine, but they don't look as good. And the other is you can display lines as polygons with these shaders that control how the junctions work and what the width is and so on. And there's some really cool stuff you can do with that. Like you can make the edges anti-aliased, you can do dashes and dots, and just all sorts of fun stuff. So this is an example of that. We had wide vector support in previous versions of the toolkit, but it was rewritten for the latest version, and it really is starting to look pretty good. Now, when you talk vector maps, you also need to talk about vector tiles. And vector tiles is sort of an open-ended term, but what it probably means these days is Mapbox vector tiles, and this is a specific data format. So it's proto buffers with specific data inside that format, which turns into points, lines, and aerials, and can also contain images as well. So when people think of Mapbox vector tiles, they also tend to think of the style. So that you got to break it into 2 pieces. There's the data itself, which is the points, lines, aerials, and images, and there's also the style information, which turns all of that data into a visual form. Now, we can handle and have been able to handle the Mapbox vector tile format for a while. The style format is more in flux. Now we support an older way of doing styles, Mapnik XML. We support the newer way of doing styles, but not to the same degree. And we also support a roll your own approach. And I'll give you examples of each. This is Gaia GPS. And in this case, they have their own Mapbox vector tiles. So they generated the vector tiles themselves, and they're displaying them using a Mapbox XML-based style. This is contour lines, but they can also do streets and other things like that. This is an example of vector tiles using the Mapbox GL style support. So they have these style sheets which you can edit in their tools. They really look great. We don't support a lot of their features, so we do the basic stuff, but we don't support their sprite sheets or their transitions or some of the fancier shader support. So the maps that result are lacking subtlety, and it's something that we'd like to correct. But honestly, if you're displaying Mapbox maps from their data sources, then you're probably using their toolkit. So we have limited opportunities to add the rest of the Mapbox GL style support, although it would be pretty easy to do if we have users who want to do it. And lastly, here's using Mapbox vector tiles with a custom style. And this is National Geographic World Atlas. And what we did here is we stored the data on Mapbox's cloud service. We're fetching it on the fly. And these are vector tiles, believe it or not. So they contain a low resolution image for each tile. And on top of that, we've got points for the symbols, the airports, things like that. And then we've also got points that describe the text placement. Now, National Geographic, being National Geographic, has a lot of different text laid out in very specific ways. But believe it or not, this is all vector tiles. And this is an example of using the vector tile format, but doing something very custom with the style. We're not using any of the standard style sheets here. We have code which interprets everything. Now rolling back to the more general vector map support, we're also going to add support for GeoPackage, which is a SQLite database that holds geometry and images. It's more flexible, it allows searching, it's an older format. And we're going to pair that with styled layer descriptor format, which is kind of a more general styling scheme, which is supported by a lot of different packages like QGIS or ArcInfo, things like that. As far as Android support, the vector tiles are coming soon. And as for GeoPackage and SLD, those are not yet scheduled. So let's talk map projections. Now, you're probably familiar with Web Mercator, which is a map projection that we all know and know. And it's basically, it's what we use on the web. It's kind of hideous at the poles, works well closer to the equator. We're all sort of used to it. But it's not the only map projection that the toolkit can support. And here's an example of doing a 2D map where a data source is coming in British National Grid, which is a custom projection that covers the British Isles. So we can do that. We can also do a map that is itself in British National Grid and has a data source, again in BNG, but also a data source in the background, which is Web Mercator. And that's trickier than it looks because we have to be able to throw out tiles that are outside the boundaries of the projection and make use of the ones that overlap. And you can do that now. We can also do a custom projection on the globe as well. And I'm happy to say that all of this is available on Android too. Now in the future, there's a few bugs related to projections. We'd like to give the user better feedback on when the core library that does the projections fails, and detect missing offset files and things like that for really high resolution cases. So back to 3D for a moment. In the last version of the toolkit, we added atmosphere, and in 2.5 there are some tweaks to that. So there's atmosphere and a night-day shader, which is really quite lovely. This is useful for whole Earth apps, or if you want to get a more accurate, this is how the Earth actually looks sort of feel. We've added sun and moon support, and that by default the sun texture is just pulled from one of NASA's images, and it kind of looks like it's going to destroy the Earth at any point. So obviously you can replace that with your own. And I'm happy to report that that's all available in Android as well. Now the toolkit has done lots and lots of screen markers and labels. That's what we're looking at here, are markers, for a long time. We switched to a shader-based approach to do these, and that really accelerated their drawing and let us do a lot of interesting things. One of those things that we did is to let those markers move in real time, and labels as well. And this is an example from that National Air Traffic Control System app, where they're displaying an enormous number of markers, all the air traffic, commercial air traffic, I should say, over the US. And all of those are all moving at once. It's implemented in the shader, and it's very, very fast. There's some cool things that we're doing with this as well. At the moment, moving objects are not available on Android. We're kind of waiting for somebody who needs that. Where we'd like to take it in the future is this. Now, particularly for aviation users, they like to build up these complicated symbols. There will be some custom text, some more text, maybe a couple of shapes, and an icon, and they'll render all that into an image, and then they'll stick a whole bunch of those images on the screen. And it's just a heinous waste of memory, because the toolkit can display all of those things individually a lot more efficiently. So what we're letting people do, starting to let people do, is to build all that up, sort of like we do with a model builder. Build it up element by element, make use of our glyph engine so the text is nice and efficient, and our icon display and things like that, and control the results as a single object. Now it's partly there for billboards. You can build up this screen object and generate a 3D billboard for that. And it's coming for 2D objects as well. That's kind of the direction we want to take it. So here's a neat feature for the 2D map as well as the globe. Marker clustering. Marker clustering is pretty straightforward. You take a bunch of markers. If they overlap, you group them together into bigger groups, and then you display some number or symbol that indicates there's a bunch of markers there. But ideally, you'd like the markers to break apart as you zoom in, and when you zoom out, you want them to reform. And we implemented this using the marker animation from an earlier slide. So it's nice and smooth and very, very fast. And you can have an enormous number of markers all doing this at once. It's really quite lovely. And it works on the globe too, which is pretty amusing when you get to the edges of the globe. At present, marker clustering is not available for Android. Would be easy enough to port though. Now here's a very, very specific feature for weather apps. This is particle system support. And particles, in this case, we're using the particles to display wind vectors. So we've got a collection of tiles that describe wind all over the US. We're looking up into those tiles and generating particles based on that. Particles are really easy to draw. They're just points with vectors, a little bit of color information. If you want to get fancy, you can make them shapes, but they're really easy to draw. The hard part is to feed them. And in this case, what we're doing is we're taking samples over the screen, maybe about 500,000 particles for this example, figuring out where those land on the Earth, and then looking up the wind data corresponding to that location, generating the velocity and the color that corresponds to that. And we're doing that about every 100th of a second, updating several thousand particles at once. And that's the difficult part of using particles, is that you have to update the data as you go. Can't be too slow. Got to get it done every 100th of a second or so. Now there's an example in the Auto Tester app, and that's what we're looking at here. So you can use that for your own particle needs. And it's also available on Android. Now one thing that we found was that Java is too slow to update all the particles itself. It spends a lot of its time, for example, on the random number generator, and it's just generally slow. So if you want to get the same density of particles, which the device can actually handle, if you want to get the same density of particles you get on iOS, you need to drop down to the C++ interface to do it. So here's another fun 3D feature that we've added, pageable 3D point clouds. And what we've got here is a LiDAR data set for somewhere in California. And these are points that are collected by, and this is probably aerial, and then glommed together into one big data set. So we've got spatial information about where it is. And then we converted those points into a SQLite database. As you can tell, we like SQLite, where each tile is a collection of 3D points, about 20,000 3D points in the LAZ format, which is a nice open compressed format for LiDAR. Then we're paging those points in as needed and displaying them. And you can see them paged. It's a lot of data to load in and decompress and put them in the right place and then display them with their colors. That's a neat feature. At this point, point clouds are not supported on Android. So let's talk about a boring but important feature. For testing the toolkit, we've added an Auto Tester app. And what this is a collection of functionality where you select something, it'll show you that function. And we use it for testing. Basically, when we add a new piece of functionality, we add a new entry to the auto tester, and then we use that to develop it and make sure, hopefully, that we haven't broken anything else. This is also available on Android and has been a big help in trying to move functionality over to Android. Essentially, we'll move a piece over, make an entry in the auto tester, and then use that to make sure it works. Where we're going to take the auto tester is to use it in continuous integration. So what we'd really like to do, we're going to try to move to nightly builds and change-based builds and do a binary distribution every night. We have a binary distribution, but we have to update it manually, so it tends to lag the other versions. And then we're going to try to do some automated device testing using a Mac Mini in my office, where we've got a bunch of Android and iOS devices plugged in. We'll run the auto tester and then send the results to the developers. That's the long-term goal. So let's talk briefly about the Toolkit architecture. There's a core C++ library that does all the rendering and all the object management. That interacts with OpenGL ES. And then on top of that, at least on the iOS version, there's an Objective-C interface, which most people use. And then obviously you can use Swift on top of that as well. We started writing a lot of tests in Swift, so it seems to work quite well. Now this was nice for porting to Android because we were able to take the C++ core, start building a Java native interface on top of that, and then redo all the high-level objects in Java. And this is kind of the downside, is that each version of the toolkit needs to work in the native grammar of the local device. So if you're on iOS, you use Objective-C or Swift. If you're on Android, you use Java. And we found it's unacceptable to expose the C++. That's just something that users will not stand for. Learned that early on iOS. So the nice thing about the Android interface is that it's all Java and it's all very friendly. It uses objects that you're familiar with for fetching data. It uses just Java idioms that make a lot of sense to Android users. But that means that every time we port the toolkit, the core moves over pretty easily, but the high level needs to be rewritten. And the reason I mention this is we get asked a lot about porting to other systems. So iOS and Android are our core mobile systems. Those are the ones that we put effort into, the ones that we spend money on. Windows Phone is a possibility. People have been asking about that, particularly with the unified Windows and Windows Phone approach. That might be interesting, but somebody will have to pay for it. Been asked a lot about desktop operating systems. Windows is appealing just because there's a lot of embedded systems based on it. Mac OS X is actually pretty easy, but there's not a lot of demand for it. And then Linux would be interesting, but it would require its own high-level C++ interface. And I know that may seem weird because the core is written in C++, but that's a very low-level interface. All the threading, all the data fetching, all of that great stuff is done in the high-level interface, and we don't have one of those in C++. We've also been asked about doing a web browser version, JavaScript and WebGL. This wouldn't really be a port so much as a complete rewrite. I'm not deeply thrilled by that, but if somebody makes a compelling case and pays for it, we might consider it. So there's some great resources available for the toolkit. There's a nice set of tutorials, reference documentation, and the GitHub issues are where we communicate with users, and there's an active community watching those and answering them. And here's the contact information for the toolkit and Mousebird Consulting as well. We're not hard to find. If you just type in WhirlyGlobe, you'll find us. And that's all we've got. Thanks for listening.